guys, it's Miss Maneely. I want to apologize. My smartboard crashed on me while I was trying to record the last lesson, so I'm going to have to do it into two parts. So if you haven't already had a chance to start example 2, I would like you to try it on your own before watching this video. So if you haven't started it, if you could press pause and just start number 2. Take a close look at it, though, because it is a little bit different from number 1. First of all, you're not given the data, so you have to use the stat option, and you're going to enter in the mean and the standard deviation that way. The other difference is that in this problem, if you read it carefully, the standard deviation of the population is not given to you. So this is a situation where you're going to have to use the t-distribution to solve. So if you could pause the video and just try the problem on your own at first, and then I'll go over the answers in just a second. Okay, so in number 2, it says, in an earlier example, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. This is a problem I believe we looked at when we were dealing with sampling distributions, and actually might have even done it with confidence intervals. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. And a simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. So because both of those values are given to you as part of the simple random sample, you know that they're describing the sample and not the population. The question is, do the data give convincing evidence that the new batteries last longer on average? So the first thing we want to do, anytime you're asked about convincing evidence, you're asked that they're basically asking you to do a test of significance or a hypothesis test. So we're going to start out with our null hypothesis, and that would be, and I'm typing, so I don't have access to all of my equation editor that I usually use, so I'm going to be typing out in words. So the null hypothesis here would be that the mean, mu, is equal to the old batteries, which would be 30 hours. And don't forget, when you're dealing with a mean, you have to include your units. The alternative would be that the mean, and we're looking at this lasting longer than the old batteries. So it's going to be an upper tail test. And don't forget that in our first step, the other criteria is to define your variable. So we're going to say that mu is equal to the mean number of hours of battery life. Okay. All right. Next thing we want to do is just verify that all of our conditions have been met, and if they haven't, we're going to have to state the assumptions. So the first thing we want to do is look at, is this a simple random sample? And we are told that it is a simple random sample, so we'll go ahead and just say SRS. And I don't have a check mark, so I'm just going to put a little asterisk to say that it was checked. I also want to look to see about the normal condition. So either the population is normal or I have a large sample. But if you look at the problem carefully, our sample is only 15, so that's really not large enough for our sampling distribution to be normal. And also it doesn't tell us that the population is normal. But if you think about it, this is a production process. We're dealing with a lifespan of batteries. It is reasonable to assume that the population is normal. So even though it's not stated in the problem, this is an appropriate assumption to make. So you want to write the word assume in front of your population is normal. And lastly, we also want to make sure that our population is large enough so that if we're sampling without replacement, we don't have that 10% issue. And in this case, again, because we're dealing with a production process, it's an infinite process. So sampling it without replacement isn't really a problem. But to be on the safe side, it's a good idea to just say that the population is at least 10 times your sample size, which is 150 batteries. That is completely, excuse me, that is completely reasonable to assume. I'm just going to abbreviate that. Okay, the next thing we want to do is talk about the type of test that we're conducting. And we only have one sample of batteries. And again, because I'm dealing with a mean, I'm either going to be dealing with a normal distribution or a t-distribution. And in this case, because I don't know the mean of the population, I have to use a t-distribution. So I'm going to be doing a one sample t-test. And if you want to do it by hand, then I'm going to do that over here. I'll just say it is I'll be using a t-distribution, and I'll need to describe the parameter of interest. In this case, with the t-distribution, it's always going to be the degrees of freedom. And in this case, since 15 is my sample size, the number of degrees of freedom is just going to be 14. So let's continue with the one sample t-test on the calculator. And I apologize, I'm using my old school TI-83 Plus, but it does everything I need it to do. So if I go into my stat menu and go over to tests, I'm going to choose the t-test this time. And I don't have the data, so I'm going to go ahead and choose the stats option. And I'm going to go ahead and enter everything. So the null hypothesis is that the mean is 30, so I'm going to type in 30. My sample statistic is 33.9 with a standard deviation of 9.8, and I know my sample size is 15. I'm doing an upper tail test, so I'm going to go ahead and hit calculate, and the calculator will give me everything I need. So I'm going to say the wrong thing. So I'm going to type in the probability. I'm always looking first at the probability of my sample result, so that's X bar. I'm just going to type it out. And I'm looking at X bar being greater than 33.9. And now I'm going to translate that, and this time, because I'm not dealing with a normal distribution, I'm dealing with a t-distribution, I'm going to say that that is equal to the probability that t is greater than, if you look on a calculator, it'll tell you 1.541. And the calculator also gives you your probability, which is your p-value, 0.0728. Okay, if I wanted to do this using my t-distribution, so this would be the alternative, and actually let me just do this down here. If I wanted to use the t-distribution and do it by hand, I am going to still need to find the mean and the standard deviation of X bar. So the mean of X bar, and I'm just typing it out because, again, I don't have my equation editor, is just going to be 30 because that's what we said it was. That's the mean of my population, or at least what we're assuming to be true. And the standard deviation of X bar is going to be the standard deviation of my sample instead of the population. It's going to be the standard deviation of my sample, which we said was, I believe, 9.8, divided by my the square root of my sample size. So again, I'm just going to type this out. And the sample was of 15. So if I'm going to find my t-test statistic, what I would normally do is say that t is equal to, I'm going to take my X bar value, subtract the mean, and actually let me put that in parentheses, and then I would divide by the standard deviation. So this is the same calculation that I would do, I'm going to put that in parentheses too, if I were calculating the z-test statistic. Okay, so on my calculator, let me quit out of here. If I were to do 33.9 minus 30, and then divide by, I'm going to put that in parentheses, 9.8 divided by square root of 15, notice that gives me my t-value. The 1.541 gives me the same number. To calculate the probability, now I'm not going to go into my normal distribution. I have to go into my t-distribution. So if you go to your distribution menu, you're actually going to choose a t-CDF. Now I've got the old school calculator, so I have to actually enter the parameters in order. And I always start with my lower bound. The lower bound in this case, since it's a greater than, is going to be the t-value, the 1.54. So if I hit second answer, it's just going to paste that in there for me. And then I need my upper bound, which is just going to be infinity. And then for the t-distribution, the only parameter it needs would be the degrees of freedom. So my n is 15. That means my degrees of freedom is 14. And that's how I'm going to find my probability. And so notice you get the same probability, 0.07228 if you round. Okay, so you can either do it by hand or you can do it using the calculator. So all of this is what I did by hand. Okay, so the last thing then is just to state our results. Since 0.07, sorry, my dog is crying because she hears me talking and she thinks I'm talking to her. Stella, shh. So since my p-value is greater than 5%, I know the result is not significant, and we cannot reject the null hypothesis. say null, not num. And so in conclusion, since we're talking about whether or not this new AAA battery lasts any longer than the old one, since I can't reject the null hypothesis, we do not have enough evidence to conclude that the new battery, or the new AAA batteries, last longer than 30 hours. Okay, and so that's how you would do a one-sample t-test. It's essentially the same thing as doing a one-sample z-test, it's just you're using a different command instead. And so you're only going to use this type of test when you're dealing with a situation where you don't know, when you're dealing with a mean and you don't know the population standard deviation. All right, I'm going to pause the video for a minute, and what I'd like you guys to do is to take a look at example 3, and just do part A. I think part B starts talking about a confidence interval. Just do part A for me. You don't have to write it all out, but just go ahead and check your calculations just to make sure that you're entering everything in the calculator properly. I'm going to press pause, and I'm going to take my dog for a short little walk, and I will be back to go over the answer and also to go over problems 4 and 5. Okay, so hopefully you've had a chance to do number 3. This is another company dealing with batteries. It's a different battery, though. It says a company has set a goal of developing a battery that lasts 5 hours or 300 minutes in continuous use. In a first test of 12 of these batteries, sorry, that's my dog seeing something outside. We've got the following lifespans that were measured, and basically we want to know if this is evidence that the company has met its goal. So it's to perform a hypothesis test and then check for conditions and assumptions. So I'm just going to kind of do this out loud. Our null hypothesis, well, at least start this. Our null hypothesis in this case is going to be, again, that the mean is equal. In this case, it's going to be 300 minutes. And we want to know, and this is actually, the way it's written, it's a little bit unclear about which direction you want your inequality to go. If you think about like a battery company's goal in terms of battery life, it really wouldn't make a lot of sense for the mean to be less than 300, because we certainly want the batteries to last as long as possible. So the alternative that would make sense here, because remember the null hypothesis is always an equal sign. The alternative that would make sense here, even though it's not really clear in the problem, would be that the mean would be greater than 300 minutes. Because, you know, the company doesn't want their batteries to last less than that. In terms of the conditions, it doesn't state that it's a simple random sample, so we'd have to actually say that we're assuming it's a simple random sample. And it also doesn't say anything about the population being normal, and this is a small sample, so that would need to be true if the data is, if we're going to be able to use a t-distribution, which in this case we're going to have to. So one of the things you should do when you have the data and you have a small data set and you're not told that the population is normal, is to construct a normal probability plot. So if you go, I have all my data in list 1, so if I go into my stat plot menu, it looks like I've got all my plots on, so let me turn them all off. And then we go back into that menu, and what I'm going to do is I'm just going to turn on plot 1, and I'm going to select, it's the very last plot option, and that is your normal probability plot. And I'm going to call up list 1, and it asks about the data axis. You can just use the x-axis, that's fine. And let me just make sure I don't have any equations stored in there. Great. So I'm going to go ahead and do zoom 9. And you can see that the data, when I do a normal probability plot, it is relatively straight. So if I were doing this on like the AP exam or on your test in my class, what you'd want to do, I'm actually just going to cheat here. What you'd want to do is sketch a picture of this graph. I didn't mean for it to go on another page. Oops. There we go. But you would want to sketch a picture of the graph and then explain what it means. So I would say something like the normal probability plot shows the distribution is approximately normal. And I will say with the AP grading, you want to be careful about saying something is exactly normal. Always kind of throw in the approximately just to cover yourself. Okay, so we've got the simple random sample, we've got our normal condition. The only other condition we would have to check is to make sure that the population of batteries is greater than 10 times our sample size. And again, I believe the sample this time was of size 12. So we're talking about 120 batteries, which is totally reasonable. Okay. The next thing we're going to do is go ahead and do the test. So if we go to Stat and then over to our test menu, again, because I'm not given the standard deviation of the population, I'm going to do a t-test. But this time we have the data, so I'm going to choose that option. My null hypothesis is 300 minutes. The data is in list 1. The frequency is list 1. I didn't enter it in as a frequency table. And since I'm doing an upper tail test, I can just go ahead and do calculate. And that gives me everything I need. So the probability in this case is going to be that X bar is greater than, and luckily the calculator does that all for us, 307.833. And then I'm going to set that equal to the probability that this time we're dealing with a t-distribution is greater than 0.9582. And then I can write my p-value, which is 0.179. And obviously that value is not significant, so we do not have enough evidence to reject the null hypothesis, and we can't conclude that the batteries last more than 5 hours, more than 300 minutes. So if it's asking if the company has met the goal, we don't have evidence to conclude that the battery life is more than 300 minutes. So it doesn't look like they've met the goal if they want it to last at least 300 minutes. And so you want to make sure when you're stating your conclusion that you're also answering the question that's being asked of you. Okay, so I'm going to ask you to go ahead and we'll do a confidence interval later. I do want to just kind of talk a little bit about how you can set a rejection region. So in number 4, it says we're returning to the battery problem for number 2, but we're also given a little bit more information this time. So from previous experience, the company knows that its regular AAA batteries follow a normal distribution. So we didn't have that before, and this time we do. So we know this time we have a normal distribution. We know the mean is 30 hours of continuous use, and this time we are given a standard deviation. And so that is actually the standard deviation of our population. So we're actually now moving back to a standard normal distribution. We can use the normal distribution, not the t. So suppose the battery decides to carry out a test of significance based on a simple random sample of 15 batteries and uses a 5% significance level. If our sample result is much more than 30 hours, we're going to reject the null hypothesis. And the 5% significance level tells us to count results that could happen less than 5% of the time by chance if the null hypothesis is true. As evidence that it's false. Anyway, that's kind of a tongue twister. Now this is asking a different question. How large would the sample mean need to be to reject the null hypothesis? So if I'm a company that manufactures batteries and I'm doing like a sample every hour to make sure that the batteries are in compliance, I don't want my assembly line workers to have to do a test of significance every hour. Instead, what I'll do is I'll do one test of significance and I'll determine what means are significant ahead of time. And that way, when my assembly line workers gather their sample and test them, they'll just have to know if the mean that they find crosses that line. And this is what we do. This is basically just called setting up a significance level. So if we assume that the null hypothesis is true and that the mean is 30, we want to describe the sampling distribution of X bar. I'm going to try to write this out just because it is going to be a little bit easier for me to write it, but when I use my slate at home, it's a little bit messier. So basically, what I'm saying is that, first of all, we have to make sure that all our conditions are met. And so, is this thing working? All right, so I want to make sure that all my conditions are met. So we're told that it's a simple random sample. We're told that we're taking a simple random sample. Let me change my pen color. All right, so we know it's an SRS. We're also told that the population is normal. We didn't have that information before, but we do now. Sorry, my handwriting is horrible on this thing. We know the population is normal, and I also know that the population is going to be greater than 150 batteries. That would be 10 times 15. Okay, and so that means that X bar is then distributed normally, since we know the standard deviation of the population is whatever it was 2.1 hours. So the mean of my population, or the mean of my sampling distribution, is just going to be 30 hours, and the standard deviation is going to be 2.1 divided by the square root of my sample size, which we said is 15, I believe. Let's double check. Sorry, that chomping in the background you hear is my dog keeping me company while she chews on her bone. All right, so now that we know the sampling distribution of X bar, let me go ahead and actually calculate that standard deviation. 2.1 divided by the square root of 15. Sorry, I know that noise is really annoying. So I know my standard deviation is 0.542. All right, so in part B, you're asked to mark the distribution. So what I would do then is I would just have my mean, and actually let me type this in because otherwise it's going to be really messy. So my mean is going to go in the middle. We know that's going to be 30. And what I'd want to do is I'd want to take my mean plus the standard deviation. Actually, let me go ahead and save my standard deviation in a variable. I'm going to call it alpha A. So what I'm going to do is I'm actually going to scale my distribution now. So I want to do 30 plus the standard deviation. We've done this before. We did this actually at the very beginning of the year when we were first learning about normal curves. So the second standard deviation would be 30.542. And then if I add another standard deviation to that, the next one would be 31.08. And I'll adjust these so that they are where they belong. Let's see. There we go. And if I do one more, then I know my last one is going to be 31.627. Okay. Well, since this is an upper tail test, I really don't care about any of the values that are below my mean. You can certainly do 30 minus the standard deviation and finish filling it out. But we said, if we look back at the original problem, that we're doing this at a 5% significance level. So what I need to do is essentially figure out the cutoff on my axis where the 5% is going to be. Since this is an upper tail test, so basically what I want to do is figure out my rejection region. I want to figure out where to draw the line at 5%. So what X value is going to be the limit for me. And so in order to answer this question, we're going to have to rely on our inverse normal calculation. So basically what I'm going to do on my calculator is I'm going to look up the corresponding Z value, because we're going to look at the Z test statistic first, and then determine my X bar from there. So if I go to my inverse normal distribution, the area to the left is what I'm going to enter, 5. And that gives me a Z test statistic, or a Z statistic, and I'm running out of room, so I'm just going to do this in part C. So that tells Z would equal 1.645. And if I want to find the corresponding X bar value, I'm just going to use the equation where 1.645 is equal to X bar, which I don't know, minus the mean, which we said is 30, divided by the standard deviation, which turned out to be 0.542. So to solve for X bar, I'm basically going to take my 1.645. I'll just type 1.645. Oops. Let me get back to my computer. And I'm going to multiply by my standard deviation. Oops. And then I'm going to add the 30. And that is going to give me an X bar value. So X bar is equal to 30.89. So basically, wherever 30.89 is, anything above that value means that I have enough evidence to reject the null hypothesis. Now, one of the things that will have to be true is that we're only dealing with samples of size 15. So let's see. So for random samples of size 15, if the sample mean is above, what did we say, 30.89 hours? Minutes, what was that? That must have been hours. So if the sample mean is above 30.89 hours, then we can reject the null hypothesis, or that we have enough evidence. Okay, and so what we've done is we've established a rejection region. So that's what this is called. This is called the rejection region. And so if I establish that ahead of time, especially if it's something that I'm going to be doing over and over and over again, like if it's a quality control purpose or production process, I can kind of set the rule ahead of time, and that way I'm not having somebody have to perform the same hypothesis test over and over and over again. We just perform it once, we determine the rejection region, and determine a rule for rejecting the null hypothesis based on that sample. Okay, in number 5, it's essentially the same type of thing, except this time you're dealing with a two-tailed test, so you have to be a little bit more careful when you're doing your rejection region, because when you're looking at your normal curve, oops, this is actually really funny. So my dog just turned off, just sat on the remote and turned on the mute, or turned off the mute. She just freaked out. Anyway, so if I'm dealing with a two-tailed test, in this case we're looking at the mean diameter of this particular bearing is supposed to be 2 centimeters. We know the diameter is normally distributed with a standard deviation, and I don't have the sheet here, but for whatever reason it didn't print. When a lot of the bearings arrive, a consumer takes a simple random sample of 5 of them, and so we want to make sure that the ball bearings, or whatever the kind of bearings are, we're looking to see if they differ from 2 centimeters. So this is going to be a two-tailed test. My null hypothesis is going to be that the mean is equal to 2 centimeters, and the alternative would be that the mean is not equal to 2 centimeters. So when I'm doing the rejection region here, I have to be a little bit more careful. So I'm going to try to sketch a normal curve here. Okay, because if my significance level is 5%, I've got to split it. So I'm looking at 2.5% on the lower tail and 2.5% on the upper tail. So I'm going to find the negative z value, and you can find both z values this way. So this time we're, again, just going to use the inverse normal curve, or the inverse normal command. And the lower probability is 0.025. And that gives me a negative 1.96 as my z value. And then again, you can find the sampling distribution for x bar and solve for x bar. The calculator also allows you to, especially the newer ones, where you can actually type in the mean and the standard deviation. So you can type in the mean and the standard deviation of x bar if you want, and it'll give you the values. If you want to find this upper part, then you've got to think about the entire area to the left, which is going to be 97.5. So if I do the inverse normal command for 97.5%, notice I'm just going to get the positive z value. So if you type in your mean and standard deviation of x bar, it'll allow you to determine the rejection region. And so basically, we're going to be rejecting x bar anytime it's less than a certain value or greater than a certain value. One of those numbers will be less than 2 centimeters, one will be more. And then the last question basically is just asking a type 1 error is when we reject, sorry, I don't know why some of the stuff didn't transfer over. When we reject the null hypothesis when in fact it's true. So what would be the probability of making a type 1 error? Well, remember, it's always the same as our significance level. Okay, so I think that's all of the examples that we had today. A couple of things about using tests wisely. One thing to be really careful of is if you have really, really large samples, then just about any difference is going to appear to be significant. So you want to also think about practical significance if you're dealing with really large samples. because obviously, even the slightest difference could be significant if you're dealing with a sample of 10,000 of something. So you also want to kind of consider, is the difference important? And of course, anytime we increase the sample size, that is going to increase our power of the function as well. All right, so for homework, there's another worksheet on tests about a population mean. It's going to include both the t-distribution and the z-distribution, so make sure you read the questions carefully. And if you have any questions, obviously, please come into Bulldog Block on Friday and I can help you. Do expect that we will have an AP drill next class as well as a review, and you should expect to start seeing some tests of significance that are going to be collected as a quiz grade.